organizers, Biplab, Rashi, and Jyotsna. I can't see her here, but for inviting me on this wonderful occasion of Professor Ramakrishnan's 60th birthday. So unfortunately, I never had an occasion to interact personally with Professor Ramakrishnan. But nevertheless, I mean, I've been working on a modular forms of half integral weight, new forms. So I've been able to meet him through his papers. So yeah, okay, yeah. So my video was not there, so I've just yeah, okay, good. So I think okay, and yeah, so I would like to congratulate Professor Ramakrishnan. So yeah, very happy birthday and many happy returns. Okay, so let me begin. So I'm going to speak on local Heke algebras, particularly with level p squared, p is a prime, GL2 type, GL2 QP, and we'll see some consequences. We'll describe the Heke algebra and see some consequences. Okay, so let me define the things we're going to work with. So let G be a locally compact p-adic group, S be a compact subgroup, gamma be a character of S, and let's define the Heke algebra to be consisting of, so G modulo S with this character gamma, consisting of all locally constant compactly supported functions on G, which are bi-invariant like this. So f of k, g, k prime is gamma k, f of g, gamma k prime, for all k and k prime in S and g in G. So this is well known to be C algebra and complex algebra under the convolution, which is given by this. So over here we are taking an so this is a Haar measure on G. So okay. So we want to study G and which with respect to some S and gamma for different choices of S and gamma and G. So let me begin with the what I call integral weight case. So let's look at G equal to GL to QP. So fixing a prime P. S is this K naught P to the power N. So matrices of the form A, B, C, D in GL to ZP with C in P to the power N ZP. So that's what corresponds to gamma naught P to the power N. And this character gamma to be just identity character to start with. So let xg be the characteristic function of the double coset corresponding to G in K naught with respect to here. So K naught P to the power N, G, K naught P to the power N. So then because the way we have defined our local Heke algebra and because we are taking the characters, the small gamma to be 1, the Heke algebra is as a vector space, it is spanned by this characteristic function chi g or xg, where g varies over all the double coset representatives. Okay, so let me also introduce some notations which I'm going to use throughout. So for T in QP star, dt is this diagonal matrix T001, WT is this anti-diagonal 0, -1, T0, ZT are the central elements, and for S in QP, I have XS denoting this unipotent of a triangular matrix, and YS denoting this 1, 0, S1. And let Z, capital Z, be the subgroup, the center consisting of all the ZTs, and N be the subgroup consisting of all this XS. Okay, so that's good. And now let me come to sort of a first case. So we want to look at the case which is the first case when n equal to 1. That's the Iwahuri's case, Iwahuri Heke algebra, and that's so Iwahuri Heke algebra is known in vast generality when G is a general reductive algebraic group. But what we are looking at is only in the case of GL2. Iwahuri Heke algebra is corresponding to the Borel subgroup, and over here we are looking at the K naught corresponding. So using Iwahuri-Bruha decomposition, we can get the double coset representatives. So this is well known. So consisting of these elements dp to the power n, zp to the power m, and wp to the power n, zp to the power m. So essentially this diagonal dp to the power n's and the anti-diagonal wp to the power n's. right? And let Tn and Un be the corresponding characteristic function. Then the Iwahuri's theorem says that if I mod out by the center, so mod out by the z corresponding to the characteristic function Zp, then the presentation is really simple. It's given by these two generators U0 and U1 satisfying these relations, very nice quadratic relations. Okay, and yeah, so I'm noting one more relation which is sort of useful. So you have several relations among U0 and U1. So U0 and Ui's will generate all the Tn's and Uns. And we will see a part of it when we look at general Heke algebra modulo p square, the last part of the talk. But in the case of yeah, I'm not writing all the relations, just writing the presentation. And one of the relations amongst this Ti's, Ui's, and U1, Ti's and Ui's is that U0 is T1, U1. So that will also come into the picture later. Okay, so that's case n equal to 1. In the case when n is greater than or equal to 2, we didn't look at the full Heke algebra. So yeah, one can consider the full Heke algebra of GL2QP modulo K0 P to the power n. But we looked at it because it gets complicated, as we will see later. But we looked at what is essentially supported on GL2ZP. So that's much simpler. So we see that the double coset representatives of GL2ZP modulo K0 P to the power n for any n greater than or equal to 2 is precisely given by this 1 W1 YP squared YP to the power n minus 1. So we have this right. We have this n plus 1 generators. So and then we try to find the relations amongst the characteristic functions coming from this W1s, this characteristic function of W1s, and this y p to the power r's. So let's denote U0 with the function with the Heke algebra element corresponding to W1. Let VR be the element corresponding to the element yp to the power r. So that's 1. Yeah, that's 1, 0, p to the power r in the lower right hand side, 1. So yeah, and then so that's my U0 and VR, and I also define these YRs, which are nothing but some combinations of VR, and that's just to make the relations simpler. Okay, so we show that the Heke algebra K modulo K0 P to the power n is a n plus 1 dimensional commutative algebra. This time is a commutative algebra and is generated by this U0 and Yi's, 1 going to n, and having the defining relation given by this essentially the quadratic and the cubic relation. So U0 satisfies a cubic, as you can see, number d over here, and the Yi's are satisfying this quadratic. So have eigenvalues 0 and p to the power n minus r, and then U0 and Yi is commute. Okay, so then so now we have Heke algebra elements. We can translate this Heke algebra elements to get operators on the space of cusp forms of level n. So we have this well-known isomorphism between the space of automorphic forms of weight 2k level n and the space of cusp forms, the classical cusp forms of weight 2k level n. So we have an isomorphism between the endomorphism algebras, and it turns out that the Heke algebra, you can see the Heke algebra is somehow, so if I take n equal to p to the power nm, where p to the power n strictly divides n, I mean, so m is co-prime to p, then this Heke algebra is a sub-algebra of the endomorphism algebra of A2Kn. And so the Heke elements, the Heke algebra elements that I defined, I can use them to get operators on S2Kn. So I think this is a way it works. So like if you start with T in Heke algebra and phi in A2Kn, then T phi is given by this element T phi is in A to K and given by this expression over here. So you can, so everything you can compute nicely. Okay, so we observe that in this case, the T1. So I'm taking n equal to p to the power nm, and T1 goes to, so T1 was corresponding to this dt, right? dp, sorry, p001. So that goes to this p to the power 1 minus k up. So this u operator, up operator. So same as a operator TP, but we usually write it as UP because P divides the level, so kind of giving it a new name. So, and we have a UN, which goes to the Artkin-Lehner operator, and so that's T1 and UN, and then we see that the VRs, which are sort of new kind of elements which we observe, they can be given by this sum with the slash operators. Yeah. So yeah, so we know how the AS looks like, and as a consequence of 3, we have that. So if f is of level p to the power rm, where r is less than or equal to n minus 1, then we can show that this s2k gamma naught p to the power rm precisely sits inside p to the power n minus rth eigenspace of YR. So YR has eigenvalues 0 and p to the power n minus r, and the space S2k gamma naught p to the power rm sits inside the p to the power n minus r eigenspace. Okay, so yeah, we study these operators and their eigenspaces, and that leads us to give this sort of a criteria characterization of a new space. So let me just state the theorem. I need some operators. So when n equal to 1, so in that case we have Iwahuri Heke algebra. Let QP be the operator coming from this U0 corresponding to this W1, and so we have that because U0 is T1 U1, we have this relation QP equal to UP times WP. Okay, and QP prime, we take just a conjugate operator of QP by WP. WP is the Artkin-Lehner. When n is greater than or equal to 2, we look at this V's, these operators V's, which is coming from this YP to the power R's, and we look at the Vn minus 1, the highest one, and we look at Rp to the power n, that's the operator coming from Vn minus 1, and that satisfies this nice quadratic. And let's Rp n prime be the conjugate of Rp prime by W, this Artkin-Lehner. And then we show that, so start with an f in S2Kn, then f is in a new space if and only if f is in the common -1 eigenspace of QP and QP prime for all prime p strictly dividing n, and f is in the common eigenspace of the operators R cubed per n and R cubed per n prime for all primes q, which divides n with the power at least 2. Okay, so and yeah, is it okay? Okay, so then I just write down. So let's use these operators U1 and U2 and just kind of particular case when n equal to 4. Note this kind of a decomposition which comes from this operators U1 and U2. So I think you can recall the things coming from the shift operators. These are, yeah, it's slightly different. The U1s and U2s are not exactly the shift operators. U2 is involution, but yeah, it somehow goes into the same space, at least in this case. So I'm just noting it because we will see a sort of analog when we look at the half integral rate scenario. Okay, so so let me just move on. So yeah, so that was so yeah, as I said, we didn't look at the full Heke algebra. We just looked at the sub-algebra and derived that theorem. But let's now look at the full Heke algebra, but consider the case when p is equal to 2. So what I mean that I want to look at the Heke algebra of GL to Q2 modulo K0 4. Okay, so p equal to 2, 2 square. And we compute the double coset representatives. And the double coset representatives are given by this. So we have d2 to the power n, w2 to the power n. And then we have the combinations of this g2 and w along with the y2s. So these are the double coset representatives. Okay, and let's define the, again, I'm taking the character to be the trivial character. So I know that the Heke algebra is supported on all the double coset representatives. And so look at Tn's and Un's, Tn's coming from d2 to the power n, Un coming from w2 to the power n. Again, try to get the relations amongst these Tn's and Un's, and we see that the Heke algebra of G modulo K04, so G is GL to Q2 modulo K04, up to this Z, which comes from the set elements Z2s, powers of them, and yeah, and it is generated by these three elements, U1, U2, V, with these defining relations. So your U1 squared is 1 plus V, U2 squared is 1, U1 commutes with V, and then we have this braid relation, U2V, U2 is equal to V, U2V. Okay, so I think here you can see that I said that there are three generators, but I mean, it's essentially two generators because we can get V from the U1. But just because the relations looks nicer in terms of U1, U2, and V, I want to keep the V. Keep the V. Okay, right. So that's the Heke algebra of G modulo K04 or PGL2 Q2 modulo K04. Okay, so now I want to look at I want to go to the half integral weight setting, and instead of GL2, I want to look at this metaplectic group SL2 tilde. So let's begin. So let's take SL2 tilde QP to be, yeah, it's by definition, it's a non-trivial central extension of SL2 QP by plus minus 1. It's given by some 2 co-cycle, Kubota's 2 co-cycle. And just to sort of imagine the things, it's essentially given by this short exact sequence where you have this 2 co-cycle coming into the picture, which is sort of hidden. Okay, so that's my G tilde, and we have okay, and we also denote. So we have K naught P to the power n. So again, down looking at K naught P to the power n intersection SL2 QP. So the matrices of determinant 1 with the C entry in P to the power n ZP. And let K naught P to the power n, this overline of that, this bar, be the inverse image of K naught P to the power n. Yeah? So that's the compact subgroup of G tilde that we are going to consider. Okay, so let me now define the elements which I'm going to work with. So my WT, so I'm using again the same notation, but it's just a determinant 1, so it's kind of just adjusting the notation. So for T in QP star, W2 is 0, T minus T inverse 0. HT is a diagonal element, T 0, 0, T inverse. And I usually denote this G bar. So we have one factor, right? Plus minus 1. So G bar would denote the G comma 1. Okay, so let me look at the case when P is odd and N is equal to 1. So that's, in the case of the GL2, that should remind us of the Iwahuri Heke algebra. So let's look at what happens over here. So we have K naught P bar. It's a direct, as a group, it's a direct product of K naught P with plus minus 1. And so it's essentially here, it's K naught P. So, and we have this, so we want to define a character gamma on K naught P bar, which is a genuine character, so that the action of this second component is not just trivial. So let's start with a character of K naught P modulo K1P. That's given is the same as a character of Z mod P Z star, and use that to define this character gamma. Okay, so just take gamma tilde of A times epsilon. Okay, then we see that the double coset representatives of G tilde modulo K naught P bar, compute that this is precisely, these are the representatives, double coset representatives, as n varies over integers. Okay, so now in the case of the Heke algebra of this SL2 tilde QP, you have this character gamma, which is no longer a trivial character. And therefore it is, you have to compute the support. I mean, because we have this, in the definition of the Heke algebra, we had this bi-invariance, right, in terms of the gamma. So some of the elements which are supported on some of the double coset representatives, they might just vanish. So we have to see on which double cosets, I mean, what are the elements which are supported on, I mean, which double cosets we have support. So we see that when gamma is a quadratic character, then we have a full support on all the double coset representatives. So it's supported on HP to power n bar and WP to power minus n bar. Okay, so that's so we are going to assume the gamma quadratic character. Okay, and we want to extend gamma so that we can define gamma for these elements HTs and WTs. These are the elements of precisely the normalizer of T, the torus, the things which consist of HTs in the SL2 tilde QP. And we just define it like this. Okay, so there is a, yeah, we can define it something like that, so that it's kind of, it's compatible. And we use these definitions of gamma to define Tn and Un. I mean, we define it like this: Tn at HP to power n bar is given by this gamma HP to power n bar, and Un WP to power minus n bar is precisely the value of gamma at WP to power minus n bar, WP to power minus n comma 1. And we show that the Heke algebra. So we have quadratic characters. So we're looking at really characters of Z mod PZ star. So essentially the quadratic characters which we're going to deal with is 1 and this canonical symbol dot by P. And we see that the Heke algebra of this double cover modulo K naught P bar corresponding to character 1, this gamma tilde equal to 1, is generated by two elements, and U0 and U1, satisfying these relations. And this is precisely like the Iwahuri Heke algebra. So we get that indeed the Heke algebra which we get out of this SL2 tilde QP modulo K naught P bar with 1 is Iwahuri Heke algebra of PGL to QP. And same thing holds if you will take the character dot, this canonical symbol dot by P. In this case, the role of U0 and U1 somehow sort of interchanges, but nevertheless, we have the two generators and we have these defining relations which looks exactly the same. Okay, so that's Heke algebra when we're looking at K naught P bar. So in fact, this work was really motivated by the Loke and Sabin's work. So if I just go back over here, no, I think maybe here, this in the Loke and Sabin itself. So what they did was they computed the case when P is equal to 2. So you have K naught P equal to 2 and N equal to 2. So that's K naught 4, the K naught 4 bar. And they computed the local Heke algebra of G modulo this K naught 4 bar. And they observed that this Heke algebra is isomorphic to the Iwahuri Heke algebra of PGL to Q2. So in some sense, it's same as like the Shimura corresponding the level 4 going to level 2 sort of thing. So that's what they did. So, and that was the motivation behind starting this project. So G is yeah. So as I said, G is the same as SL2 tilde Q2. Now S instead we look at K naught 4 bar, and we can it's K naught 4 bar turns out to be direct product of K14 and M2, where M2 is the center generated by this minus I comma 1 cyclic group of order 4, and so we define. Loke and Sabin, they define gamma as a character taking minus I1 to some fourth root of unity. K14 of course goes to trivial, and then we can use this to extend gamma to the normalizer of T, and by mapping H2 to the power n bar to 1 and W1 bar to this element, the 8th root of unity. Okay, and again, so in this case they have to really check. So in this case, it turns out that the double coset representatives, when you're looking at K0 4 bar, the double coset representatives, there are a lot of double coset representatives, not just H2 and W2s. In fact, the double coset representatives corresponds to, I mean, they look exactly like this over here. Instead of D, you have H, and so you have these many classes of double coset representatives for SL2 tilde Q2 modulo K0 4 bar as well. Now we're looking at sort of determinant 1 elements, so slight adjustment, and they could show that if they take their character gamma like this, then it's supported precisely on these two types of elements. So on all other elements, the support, there's no support. So only supported on the representatives of coming from these two kind of elements. So yeah. So diagonal and anti-diagonal kind of elements, or the elements of the normalizer. Okay, so then define Tn and Un as before, and we have this Sloke and Savin. They proved that the Heke algebra is given by up to again center is given by this U0 U1 and U0 and U1 satisfying these kind of quadratic relations. Okay, and you can see that this is exactly the Iwahuri, I mean, it's isomorphic to the Iwahuri Heke algebra PGA to Q2. So that's what they call local Shimura correspondence. And so when we have just K0 P, this is a sort of a local Shimura correspondence, because I mean, when P is prime and P only divides the level only once, then we know that when we are going from the Shimura, I mean, when we're looking at the Shimura correspondence, it goes to the same, right? The 4m goes to 2m, and m is odd and square free, then 4m goes to 2m. So the P, when P is odd, we expect this isomorphism. Okay, so then we looked at the case n equal to 3, just to extend their thing and see what do we get? Do we get something new? So it says, so we take S equal to this K0 8 bar now, and we observe that if we look at this quotient group S modulo K1 H cross M2, then it's generated by H5. I mean, you can just so let's, if you can write it explicitly. And chi1 and chi2, let's define chi1 and chi2. Now we define two characters on S. So K1 8, take it to trivial. So on M2, so M2 is generated from minus I1 goes to the 4th root of unity. And then you have an H5 bar. So we take chi1 taking H5 bar to 1 and chi2 taking H5 bar to minus 1. So we have these two characters, chi1 and chi2. And then we try to see where the Heke algebra is supported. And again, I'm not giving all the double coset representatives, but I'm only giving the support. And we show that when looking at chi1, the Heke algebra with character chi1, K0 to 8 bar, it is supported precisely on the double coset representatives given by this. So you have H and W's, you have Y4s, Y4 bars, so 1401, 1, and then you have the combination of H and Y's and W and Y's. When we look at the character chi2, then we see that the support is precisely on the other double coset representatives in some sense. So you have H and W's are still there, and then you have this Y bar 2, and the combinations of H and Y2s. Okay. And actually, there are some more double coset representative which is not there, and on which both of them have no support. Okay, so corresponding to Y4, so if you're looking at HG K0 H chi1 and chi2, corresponding to Y4, we have the element V. We define the element V, and for chi2, corresponding to element y2, w2 inverse y2, we define the element z. So we have two extra elements, b and z, in the Heke algebra of chi1 and chi2. We are just taking those two extra elements apart from the usual u1, u2, uns and tns. Okay, and then we can show, so we showed that the Heke algebra of this SL2 tilde Q2 modulo K naught 8 bar corresponding to character chi1 is given. The presentation is this. You just normalize the thing, and that's the presentation we get. And if you see that, you will realize that you see u1, u2, v, u1 squared is 1 plus v, u2 squared is 1, and then we have this braid relation, and u1 commutes with v. So it's precisely the relation presentation for the Heke algebra of this PGL2 modulo K naught 4, right? So we sort of get it back. So, and same for the chi2. So we see that the Heke algebra of SL2 tildes modulo K naught 8 is isomorphic to Heke algebra of GL2 Q2 modulo K naught 4. So when we are restricting to ourselves to the character chi1 and chi2. Okay, so now this we use this elements u1, u2, v to actually try to give a new form theory. So I think, oh, okay. So, right, so I'm going pretty slow. Okay, so let me, so we have, so I think Professor Dipendra Prasad, in the first lecture, he introduced this, the Shimura lifts. So we have the Heke equivariant maps, taking sk plus half 4n to m to k 2n. And when k is greater than or equal to 2, then it's essentially it goes to S2k. And then we have the theorems of Niva and Ueda, which were the sort of first, theorem of Niva was the first step towards giving a new form theory in some sense. So they got an isomorphism. So in the case of Niva, it defines when m is odd and square free, got an exact, so you've used the traces of Heke operators to prove an isomorphism between the space of sk plus half 4m and s2k 2m. And Ueda extended it, and he proved the Heke isomorphism between sk plus half 8m and s2k 4m. Conan, he defined his plus space, which was, so Niva actually defined an operator, and this operator was precisely the operator which we looked at, coming from the U0. And Conan defined his plus space as an eigenspace, minus one eigen, not minus one, sorry, p eigenspace of that operator. So, and it somehow turns out that it satisfies this Fourier coefficient condition. Okay, and then he defined, so that's he did it for level 4, and then he extended to level 4m, and he defined a new space there. And then Ueda and Yamana, they extended the Conan's thing and to the level 8m, defined a Conan plus space at level 8m, and showed that the new space at level 8m, they defined it in terms of certain operators. Apart from the plus space condition, you have to have some operators to get the new space. And show that it is isomorphic test to Q2M. So they really combined a lot of different kind of operators to get this thing. So like a shift operator, not exactly shift operator, but the combinations of that. So so we try to use the operators that we defined earlier to get a complete new form theory, to complete the new form theory for S plus half 8m. And in fact, there is a work of Manikam, Meher, and Ramakrishnan, who gave such a theory, but our methods are pretty different, and also some of the results differ, especially in the Fourier coefficient conditions. So let me just sort of try to get the things. So we again translate all the elements that we defined in the local Heke algebra to the operators on sk plus half 4n in several cases. So m is square free. Then we're looking at p, where p divides p divides n only once, and then we have we have for sk plus half 4m, so and sk plus half 8m. So we have these operators over here and the involution. And some of the operators are involutions, so that we got involution like v. So we have this involution v4 tilde and w8 tilde. So anyway, we study, so we know the relations they satisfy, we study the eigenspaces, we show that these operators are all self-adjoint, and we have this this theorem. So that's yeah. So we get to that. So it's quite analog to the integral weight setting which we proved earlier. That suppose SK plus half minus 4m is a common -1 eigenspace of the operators QP tilde and QP prime tilde. That's precisely coming from the U0 and U0 tilde. Then we show that the SK plus half minus 4m is isomorphic to S2K nu 2m. So that's yeah. So that's not the plus. That's sort of, we call it minus. So in some sense, a new space corresponding to this 2m, and this space SK plus half minus 4m doesn't have any Fourier coefficient condition. Okay. So then we have SK, then we define, in the case of 8m, we define SK plus half minus 8m to be the common -1 eigenspaces space of the operators QP tilde and QP prime tilde coming from the U0 over here, right? And the operator and the operators V and its conjugate. So V4 and V4 tilde, and we show that the SK plus half, this common eigenspace, -1 eigenspace, is precisely Heke isomorphic to the new space of level integral weight, new space of level 4m. And we get that, so apparently the SK plus half minus 8m does satisfy the Fourier coefficient condition, and it's precisely the opposite of the Cohen plus Fourier coefficient condition. So it satisfies the condition like this. So I think that's where it's our results differed with the result of Manikam, Meher, and Ramakrishnan. Okay, so I think, and this is based, I mean, the reasoning is that essentially we use this projection. So Cohen defined this projection operator, this P8 is given by this, and so we get that our operator that we defined earlier, the involution, is essentially P8. And from the expression of this P8, we can see that the plus space is contained inside the +1 eigenspace of V4 tilde prime. Because V4 tilde is an involution, self-adjoint involution, so the -1 eigenspace would have the opposite Fourier coefficient sign, and our new space is contained inside the -1 eigenspace and therefore has the opposite Fourier coefficient condition. Okay, so that's about the new form theory. So I think in the remaining, I think so. I have at least 5 more minutes, right? So. Okay, so I think
6 minutes.
Okay, so I might take a couple of more minutes. Yeah, sorry for that. So let me just, I think I'll skip through this. I think I don't want to go through that. So yeah, so I think, yeah, so we're looking at the Heke algebras, and we went, so we looked at the PGL to, so let's go back to this PGL to Q2 Heke algebra again, and modulo K04. And so we look at the center. So essentially, yeah, it's well known due to Kasselman, Bernstein, Zelvinsky. It's well known that we have bijection between the set of finite dimensional irreducible representation of the Heke algebra and irreducible admissible representations of the GL to Q2 with the trivial central character and having a K04 fixed vector. So in some sense, we know the Heke algebra nicely. So we want to sort of try to figure out what are the finite dimensional representations of the Heke algebra and try to get information on the whatever we can get from on the irreducible admissible representations. Most of the things, some of the things are known and some of the things might be new. So we compute the central elements of the Heke algebra. Looks like C, yeah, these are essentially the generators of the center of the Heke algebra. And we use this to obtain the finite dimensional representation of the Heke algebra. So here C1 satisfies, I mean, C1 satisfies a really nice quadratic again. However, C2 has it's not finitely generated, and C1 and C2 gives the full center along with 1. Right, so we show that irreducible finite dimensional representation of this Heke algebra is of dimension at most 3. We have a 1-parameter family of 3-dimensional representation, and that precisely corresponds to the spherical representation, 2-dimensional representation corresponding to Steinberg representation, and then we have 2 characters corresponding to supercuspidal representations, and the other characters correspond to 1-dimensional representation. So we get to this kind of, yeah. And just, oops, sorry. And yeah, so, right, so we compute the Whittaker functions. We have precisely exactly 2 irreducible admissible representations with the level 4 nu vector, both of which are supercuspidal, and we compute the Whittaker function of this supercuspidal representations. So we just use this Heke algebra method. We don't realize the supercuspidal representation just through the Whittaker function. Okay, so I think probably, yeah, so I think I'll skip through. So here I'm just defining the Whittaker functions and all the actions and everything. And so, yeah, here's what we get. So let W be a Whittaker function corresponding to Whittaker function in this which has it's a K04 fixed vector. Then suppose it satisfies this condition, U1W is 0, U2W is epsilon W. Then up to a normalization, we can get the Whittaker function completely. I mean, to know the Whittaker function, because of this Iwasawa decomposition, we have to only know the value at GT, GTW1, and GTYT as T belongs to QP star, and we defined it. I mean, we get all, yeah, so we get the W up to normalization up to some scalar is uniquely determined by this. So we usually take WD1 equal to 1. Okay, so and then so that was so we looked at so that's the sort of information we could extract from the Heke algebra of GL to Q to modulo K04. So we wanted to see what happens when we look at the Heke algebra of GL to Q to modulo K0 P squared, the full Heke algebra. And we soon realized that things are not very simple, even when we are looking at just P squared. So we have these kind of double coset representatives. And then we have, so if you remember, in the case of P equal to 2, we had this element of the type, this Y, YP, Y2, W2 to the power n Y2. In this case, we have not just one, we have actually P minus 1 elements of the type. We have Y alpha P, WP to the power n YP. So when P is bigger, the things are actually more complicated. P equal to the things are nicer in some sense. So anyways, so we tried, so these are the double coset representatives. We try to see what are the relations and what can be the generating relations amongst them. And we compute, so we are able to compute all the relations and also compute the defining relations. So things becomes quite complicated with, so Tn is xdp to the power n, Un is coming from Wp to the power n, and then these are this element Dn alphas, which are corresponding to this Y alpha P, Wp to the power n Yp. So Dn alphas are like that, as alpha goes from 1 to P minus 1, and n greater than or equal to 2. So Tn's, Un's kind of element we have dealt with sort of earlier, and we get a similar kind of relations from them. But the Dn alphas are, it's a bit complicated. And so we could derive the defining relations, working out in general formula for Dn alpha, Dn beta, so that so if you look at D3 alphas, then D3 alphas essentially, so we have D2s and D3s, right? N greater than or equal to 2, and D2s and D3s along with the U1 and U2 gives us all the generators. So in fact, over here, if you see, let me just kind of take a big, So if you look at D3 1 star, D3 alpha star, D3 alpha, so take alpha to be 1. So then you can see that there is a D4 coming into the picture over here, right? D4 is coming into the picture. And if you take D3 1, alpha star D3 1, where alpha is not equal to 1, again you have D4 coming into the picture. So that gives you P minus 1 relations amongst these D4 alphas, and it turns out that so we have p minus 1 unknowns in p and p minus 1 relations, and the determinant is non-zero. So it's alpha goes from 1 to p minus 1. Your 4 alpha also goes from 1 to p minus 1. So determinant is non-zero, and so we get that D4 alphas are uniquely determined by D3 alphas. And then we have these inductive relations amongst these DNs and D3s, which gets us all the DN alphas. So that's what we get. So we have P generators, U1 and U2. U1, U2 gives us all the UNs and TNs. You see over here. So you can see that U1 and U2, for example, from number 5, U1 and U2 gives us T1 and T minus 1. And then along with 1, I get all the TNs. And then along with 3 and 4, I get all the UNs. I also get using U2. So V is the same as again, coming from the U1. So number 15 over here. And U2, VU2 gives me D21. So that's good. So then we have this relation amongst D2 alphas and D21 minus alphas. So I essentially need D2 alphas as alpha goes from 2 to P minus 1 by 2, I think. And then we have DN alphas. They're essentially DN minus alpha up to U2. So that's along with this inductive relations gives us shows that the Heke algebra is generated by this. So as in the case p equal to 3 and 5, these are optimal generators, but in the case p equal to 7, we see that this is we can actually reduce the number of generators. It's not optimal. And in the case of p equal to 11 and 13, also we saw that number of generators can be reduced. So we don't know exactly what are the optimal number of generators, and it just depends on these kind of solution of these kind of Kronecker symbols. But nevertheless, we have generators, and independently we could also compute the Whittaker function corresponding to new vector of level p squared, and that also dependent on exactly this U1, U2, and the D2 alphas and D3 alphas. So in some sense, it shows that we are in the safe. It matches in some sense. Okay, so I'm sorry for going over time. I think I'll stop here. Thank you very much.
So thank you very much, Professor Purkar, for this wonderful talk. So thank you very much. So are there any questions and comments? So this is now open for question and answer session. So are there any?
Can I ask a question, Tapas?
Yes, please, sir, go ahead.
Thank you for your beautiful talk, Soma.
Thank you.
You did the level gamma naught 4 and gamma naught 8.
Yes.
But not beyond that.
So beyond that is still we are computing. So we went back to look at the Heke algebra modulo p squared itself for p odd. So we want to do k0 2 to the power n for general n, and we did compute support in some. So there is a partial computation we have done over in that. Okay. But
and we came back. What is the story for p odd?
So the story for p odd is so we do have an Heke algebra, but we haven't computed the double cover part. We have just the integral gate part. So we have GL2 Q2, GL2 QP modulo k0 p squared. So we don't have SL2 tilde QP modulo that corresponding k0 p squared. And we expect that there should be also, something over there, and because even when we're getting the new form theory for the half integral weight case, when the prime divides with, the p odd, but p divides with a higher power, then the twisting operators and some other operators comes into the picture as well. So
the work of Savin and Locke, they do which case?
They do the case, so they do k0 4.
K0 4.
Exactly, yes.
But not p odd?
No, they don't do p odd case.
Okay. I mean,
So they don't do the case K naught P square with P odd. No.
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 I mean, you know, Shimura correspondence is between SL2 tilde and PGL2, but also
Yes.
with PD star. And somehow the complete story is not to be seen only on PGL2. You have to also take into account PD star. Did you know about this?
No.
You know, what is called the Walsh-Purgey correspondence.
Yes.
And you know, these things have been generalized by Vitek Gan and Savin. Shimura correspondence gives some kind of a bijection, not between SL2 tilde and PGL2, but between SL2 tilde and the disjoint union of PGL2 and PD star.
Okay.
So somehow I think the Heke algebra is not quite, so the Heke algebra on the metaplectic group is not fully seen by PGL2, but there is some part of it which spills over to PD star.
Okay, so
you know quaternion division algebra and what is called the Jacques-Langlands or Walsh-Purgey correspondence.
Yes, yeah. So, but in the case when P equal to 2,
this bothers one also for P odd.
Okay. So
but P odd also is a problem. I think the Heke algebras are not quite isomorphic, because you know, if the Heke algebras are isomorphic, the groups will have the same representations.
Yes. So, but
that
in
is
the
not
case
the case. That is not the case.
Okay. But in the case P equal to, like in the case of 8, we do get isomorphism. So
I'm a bit, you know, what can happen is that things which are coming from division algebra, because you are trying to take trivial central character, their conductor may be little larger. So they may not be seen there, but I have the feeling that it should be seen there also. So for gamma naught 8, you are getting some isomorphism? Yes,
for gamma naught 8, we're getting isomorphism.
I'm a bit surprised, but there was this student of Savin by name Arun. No, Arun, just one moment. Arun Wood. You know this person?
Okay, yeah.
Arun Wood.
Yes, I
so
know
he
him.
has some papers on MathSciNet. You can check that. He has one paper in MathGIS Drift, and he does look at the two-adic Weyl representation and such kind.
Yeah, I think I have looked at some of his papers. Yeah. So, okay,
Okay, just one last question. How do you think about Conan plus subspace?
Okay, so the Conan plus subspace, right. So it's the way it comes into our picture is this. So I think maybe I should sort of go to this this one, which I didn't quite come over here. So yeah, so we actually have a so if you look at we did get this kind of decomposition. So if you look at just the level 8 case, then SK plus half gamma naught 8 is given by this decomposition. And this is what corresponds with what we look at S2K4. So if you look at A plus 4, that's precisely corresponding to S2K1. And it's sort of conjugate. Okay, so I think, yeah, it's conjugate, which is what is it called? Yeah, so A plus 4 is corresponding to S2K1 and its conjugate is corresponding to this S plus 4, the Conan plus space. So I think just, sorry. Yeah, over here. So S2K gamma naught 4, we have S2K1 and QU1 S2K1. So actually I should do gamma naught 2 when I'm looking at the Conan plus thing. So gamma naught 2 will be having S2K gamma naught 1, direct sum QU1 S2K gamma naught 1. And when I'm looking at SK plus half gamma naught gamma naught 4, then I get this A plus 4 and S plus 4. So in some sense, this A plus 4 is the space which corresponds to S2K1, and that's conjugate is corresponds to the this QU1 of that conjugate corresponds to the Conen plus space. So Conen plus space, yeah, it's an eigenspace of one of this operator, but it's actually the conjugate operator thing. It's not really the exact space.
Yeah, thank you. So I think I will let others talk to you. Thank you.
Yeah,
thank you, Professor Prasad, for your nice and interesting questions. So are there any other questions? We have very few minutes left. Any other comments? Okay, so if not any other questions or comments, so we can thank the speaker again. So
thank you. Okay. So I'll just stop sharing the screen.
So we have maybe 2 minutes break.
Okay. So I'll just stop sharing the screen.
Yes, please.